Hello guys, in this video we are going to see about the topic called trees. First, there are many types of trees. In that we are going to see about AVL tree, B tree and binary search tree and last Splay tree.
AVL tree is a self-balancing binary search tree. It was the first such data structure to be invented. In an AVL tree, the heights of the two child subtrees of any node differ by at most 1. If at any time they differ by more than 1 or more than 1, tree balancing is done to restore this property. Rebalancing is done by rotations to satisfy its balancing. Rotations divided into 4 types: left rotation, right rotation, left rotation and right left rotation. The first example, we are going to see how to insert an number or element in AVL tree. It is as the same rule as binary tree. If the number is less than the root node, then it will go to left side of the root node, and if the number is greater than the root node, it goes right side of the root node. The only difference is it requires balancing to be checked each and every. This example we have seeing that 11 is not balanced, so we using left rotation to balance the 11 root node. Panel we can see that we have used left rotation to balance the root node, and we are inserting 13 into the tree. Now we are inserting 12 which have created unbalance in 11, so we using right subtree left side, that is right left rotation. Left rotation is just that we first should rotate it on right side, and we should rotate the whole root node into left side. In this example, we are seeing or inserting 8 which have created unbalancing in 7, so we using right subtree left side, that is right left rotation to solve. So we solve using right left rotation. First we rotate it on right side, we rotate the child on right side, and we rotate the unbalanced root node on left side. Now the tree is balanced. This is how we can do the AVL tree inserting.
So next we are going to see about the topic called B tree. Introduction. B tree is a self-balancing search tree. It follows the BST rule. Properties of B tree. All leaves are at the same level. Insertion of a node in B tree happens only at leaf node. So here is the notation and rule of the B tree. When the order is m, that is m is equal to 5 and m is equal to 3. So when m is equal to 5, the minimum children, that is m by 2, will be 3. The maximum children m will be 5. The minimum key, that is m by 2 minus 1, will be 2, and maximum key m minus 1 will be 4. When the order m is equal to 3, then the minimum children m by 2 is equal to 2, and the maximum children m will be 3, and the minimum key m by 2 minus 1 will be 1, and the maximum key m minus 1 will be 2. So this is the rule for the B tree. So here is the example of B tree for performing the tree of order m is equal to 3. The question is 16, 15, 13, 10, 7, 6, 4, 3, 2 and 1. First we insert number 16. Second element is 15, so that 15 is less than 16, therefore it will be on the left of 16. Third, the element is 13, so it is less than 15 and it is less than 16 also, so it will be on the left of 15 and 16. But for m is equal to 3, the maximum key is only 2, but it violates the property, so we will separate the 13 from 15 to 16. So the tree becomes as 15 as a parent node and 13 as a left child and 16 as a right child. Next, the element is 10, so 10 is less than 15 and 13, so it will be placed left side to 13. So it is 10 is placed left side to 13. Next element is 7, it is less than 15 and 13 and 10, so it is placed left to 10. So here the condition gets violated and the 10 becomes as a parent, so the tree becomes as 10 and 15 as a parent and 7, 13, 16 as a children. So we have 2 parents for 3 children. Next we insert number 6, so it is placed left to 7. Next element is 4, it is less than 6, so it is placed left to 6. Here the condition get violated and 6 becomes as a parent. So here now the tree becomes as 6, 10 and 15 are the parent node and 4, 7, 13, 16 are the children's. So the here the condition get violated. Why? Because we have 3 element here. So 10 becomes as a parent and 6 becomes as a root node and 15 becomes as a root node and 4 and 7 as becomes as a left and right children. So next we insert number 3. So 3 is inserted left to 4. Why? Because it is very small, small than 4. So it is inserted left to 4. Next we insert number 2. 2 is inserted left to 3. Why? Because it is smaller than 3. So here the condition get violated and next the tree becomes as 10, 3 and 6 as a parent for 2, 4 and 7 and 15 as a parent for 13 and 16. Next we insert 1. So 1 is inserted left to 2. Why? Because 1 is lesser than 2. So the tree ends and this is the B tree for order m is equal to 3. Next, we are going to see about binary search tree. What is a tree? A tree is a kind of data structure that is used to represent the data in hierarchical form. It can be defined as the collection of objects or entities called as nodes that are linked together and to simulate a hierarchy. Tree is a nonlinear data structure as the data in the tree is not stored linearly or sequentially. Now let's start the topic, the binary search tree. In this slide, we are going to see about what is binary search tree and how it works. A binary search tree follows some order to arrange the element. In a binary search tree, the value of left node must be smaller than the parent node and the value of the right node must be greater than the parent node. This rule is applied recursively to the left and the right subtree of the root. This is the example of the binary search tree. Let us understand the concept of binary search tree with a better example. In the previous picture, we observed that the root node is 40 and all the nodes of the left subtree are smaller than the root node and all the nodes of the right subtree are greater than the root node. Similarly, we can say the left child of the root node is greater than its left child and smaller than its right child, so that it also satisfies the property of the binary search tree. Therefore, we can say that the tree in the previous image is a binary search tree. Suppose if we change the value of node 35 to 55 in the previous tree, check whether the tree will be a binary search tree or not. In this picture, the value of the root node is 30, which is greater than the left child, so it satisfies the BST. but its right child is greater than the root and the parent node, that is the number 55. Before adding 55 to the right side of the 30, check the number 55 with the parent node and the number 30. Here the 55 is greater than the parent node 40, so it goes to the right side of the parent node and it becomes the right subtree of the root node 50. Why? Because 55 is greater than 40 and greater than 55. So according to the rule of the BST, the greater number should go to the right side of the parent node. So the 55 goes to right side of the parent node 40 and goes to the right of the 50. Next, we are going to see searching in a binary search tree. Searching means to find or locate a specific element or node in a data structure. In binary search tree, the searching a node is easy because elements in BST are stored in a specific order. The steps of searching a node in a binary search tree is listed below. First, compare the element to be searched with the root of the element of the tree. If the root is matched with the target element, then return the node's location. If it is not matched, then check whether the item is less than the root element. If it is smaller than the root element, then move to the left subtree. If it is larger than the root element, then move to the right subtree. Repeat the above procedure recursively until the match is found. If the element is not found or not present in the tree, then return to null. This is the pictorial representation of searching in the binary search tree. So the step 1 is the root is 45, the item is 20 and the item is less than root 2 data. So the answer will be the root is equal to root 2 left. So the 15 is less than 45, so it goes to the left side. Next, step 2, the root is 15. Then step 2, 15 will be the root. Item is equal to 20. So the item is greater than root 2 data. So root is equal to root 2 right. So the next number is 20, which is greater than the 15, which is the root. So the greater number should go to the right side of the root. So the 20 comes right side of the 15. Then it goes for step 3. Then 20 becomes the root and next number adds up. The root is 20 and the item is 20. The item is equal to root data. So the data and the root is equal. So it returns to the root. And this is the searching in the binary search tree. Next, we are going to see about the topic splay trees. Splay trees are tree structures that are not perfectly balanced all the time. Data most recently accessed is near the root. Principle of locality, that is 80 to 20 rule. The procedure. After the node X is accessed, perform splaying operation to bring X to the root of the tree. Do this in a way that leaves the tree more balanced as a whole. Next, we are going to see about the insertion of element in the splay tree. In this, we have two operations known as jig and jag. The elements which are we inserting in the tree is known as the splaying. Next, we are going to see about the deletion of element in the splay tree. So we have to find a certain element which is to be deleted and perform the zigzag operation of splaying to delete the element. So this is the deletion and insertion of elements in the splay tree.
So that's all about the topic trees. So meet you in the next video and thanks for watching us. So please do like, share and subscribe our channel. Thank you.